for the organizers for having me here. This is a really fun conference. Um, I will speak about multifractal spectrum of planar harmonic measures, and this is based on a joint work with Ilya Binder, and it's work in progress. So I can talk about this 3-4 times a year, and every time I give a talk which is slightly different because the project progresses. And I want to start by describing different aspects or different worlds of the same object. So the first world is going to be the world of conformal maps. Look at a map 5 from the to the complex plane, and secretly, I will always assume that my image is bounded. And I want to study the following set. So I will denote the set by C phi of A. This will be the set of all points on the boundary of the disk with certain growth of the derivative. So you're on the disk and you step back a little bit and you take a direction and you want to see how the derivative behaves here, right? Roughly. And I want to measure the size of this. Now I say the word size, but the word size is not well defined, right? So what options of sizes do I have? Well, the first one is the Hausdorff dimension of this set. The problem with the Hausdorff dimension is it's incredibly hard to study sometimes, even for simple maps. And so that makes us turn into something slightly easier, which is the Minkowski dimension. Let me just recall what it means to look at the Minkowski dimension versus the Hausdorff. With the Hausdorff, we fix a scale, and we're going to cover our set with disks with diameter at most that scale, right? They might be very small. So for example, the dimension of rational numbers is 0 because, right, we can cover every point with like smaller and smaller disks. However, with Minkowski, we fix a scale, and we cover our sets with disks of the same scale. So for example, for rational numbers, we'll get that the Minkowski dimension is actually 1. Which sounds kind of a bad idea to use this name, but we'll see that oftentimes this is actually very helpful because Hausdorff is hard to find and Minkowski is oftentimes nicer to find. Now, how does that relate to measuring the size of this set? So what we're going to do is, as I said, we are stepping out. We look at diameter r, and then I'm going to take this arc and I'm going to chop it into pieces. And each one of these pieces is going to have size 1 minus r. And then out of these arcs, I'm going to count the ones that contain some point that satisfies this. So this will be called the Minkowski distortion spectrum. It is denoted by d omega a. And this is the number of arcs such that you can find some point with the correct derivative behavior. Now let me stop here for 1 second and say, well, all the definitions I'm going to give today are like hand-wavy, they're not precise. And a lot of the arguments that I will say are also not going to be extremely precise, but they're enough to convey the ideas where the struggles are and things like that in this project. Okay, so this is one of these cases where it's not exactly precise. I have some error here that I allow and things like that. Okay, and now the third kind of size that I'm going to mention, this is something that I'm just going to mention by name, is the integral mean spectrum. And the reason why I am only mentioning it by name, or that I am mentioning it by name, is because this is related to a lot of fancy conjectures. So this provides strong motivation for a lot of things in the talk. For example, Brennan's conjecture is only tied to this object. And how are those related? Well, the Hausdorff dimension, it's not hard to see. It is always less or equal than the Minkowski dimension. And these two are related by a Legendre transform. Now I promised several worlds for today. This is the conformal world of today. And now let me take you to the world of measures. So for now, let mu be a general measure. And I'm going to be interested in the set W mu, which is the set of all points in the support of my measure, such that if you measure a ball centered at this point of diameter delta, this behaves like delta to the alpha. So while this set kind of tells you something about how the map phi behaves near the boundary, how it distorts near the boundary, this collection tells you how the measure decays near a specific point, right? And what rate it shrinks.
Shouldn't there be a notation with alpha there,
So it's delta to the alpha.
but on the left-hand side?
Yes, you are right. So this is W mu of alpha, precisely. And again, I want to talk about size. So one option of size is, well, I was supposed to be more centered, I apologize. One option of size is the Hausdorff, but we have the same problem. It's very hard to measure Hausdorff dimension. The other option is Minkowski. Well, here we fixed these arcs and we counted how many arcs satisfy our condition. Here, what we're going to do is we're going to look at our set. We're going to cover the boundary with disks of diameter delta. And we're going to count how many of them satisfy this condition. So in this case, it will be called the Minkowski dimension spectrum. This will be kind of roughly the number of disks of, say, radius delta with the measure of the disk being kind of like alpha to the delta. And I will denote this by F omega of alpha. And again, some name dropping. Just like we had the integral mean spectrum in this case we have the packing spectrum. Which already made an appearance in this conference in Bergweiler's talk on Tuesday. And as before, the Hausdorff dimension is dwarfed by the Minkowski dimension spectrum, and the Minkowski dimension spectrum is related via Legendre transform with the packing spectrum. Now, for people in this specific audience, I can also mention that the packing spectrum, in the case of what's called a finite iterated function system, or in particular for a hyperbolic polynomial Julia set, this coincides with the potential stuff. Right? And the measure that attains the equilibrium is the harmonic measure, which is actually our next object. So if I want to relate these two worlds, what I'm going to do now is I'm going to fix a bounded simply connected domain. My domain is going to look something like this. Now, like calling it the anglerfish domain. I'm going to fix a point. So every simply connected domain, we know that it always has a conformal Riemann map from the disk to C. So this is one object. Yes, an ellipse. And on the other hand, it also has a
Sorry, which way is phi going?
From, you're right, backwards. Thank you. And this direction is related to Levins conjecture. I always apologize. And on the other hand, it has a unique harmonic measure. Now, talking about harmonic measures, I can look at this object or think of this object, at least for simply connected domain, at least in three different ways, right? The first one is you could think of harmonic measure as the probability that a random walk starting from here will hit some part of the boundary. And this is an extremely useful perspective, especially when it comes to intuition. Because, for example, if I take this very, very small arc here, red arc, versus this, say, very long yellow arc, you can see that while the red arc is very small, the harmonic measure of the red arc is going to be proportional to its width, right? Because you only have to travel here. On the other hand, the harmonic measure of the yellow arc, even though it's a very big arc, is going to be very small because you have to manage to pass through this very narrow, well, usually narrower tube. Let me make it even narrower, right? Which is very hard to do. So this perspective gives me a lot of intuition. And this is a very key observation that we're going to get back to. This is a key observation for today's talk. All right, for people from PDEs, harmonic measure will all be the way to solve the Flash equation. I, for one, want to look at harmonic measures as the push forward of the unit measure on the circle. So you take a curve, you look at the pre-image of the curve, and you take the length measure. Now, on Tuesday, Stella mentioned that phi is not well defined up to the boundary, but you can throw away a very, very small set and it will be fine. So this definition will work. And this is the beginning where we can see that there's some connection between the decay of the map phi, or the behavior of the map phi near the boundary, and the harmonic measure. And today I'd like to show you how this connection, when it is formally true and holds, and when this connection is slightly faulty, could be gentle. But first, maybe let's say a few words about the history of this thing. So these two terms, the dimension spectrum for harmonic measures and the Minkowski distortion spectrum, were coined by Makarov in the 90s, in 98. And he had this beautiful construction between these two objects. But there seemed to be a small crack there. And today I'm going to try to describe the crack, what fails, and how in some sense we can fix it. Okay. Now, this between these two was investigated immensely by a lot of people. I will only mention one problem because Alec worked on it. And that is the problem of Littlewood's constant. So the problem is to find the optimal constant E such that for every polynomial of degree n, the areal derivative of its hyperbolic derivative is bounded by some constant times n to the e. And Littlewood presented this problem in 1952, but a lot of progress has been made using these connections and harmonic measures in the 80s. And as I said, well, Alec has at least two contributions that I know of. One is of Alec and Sodin from 88. So they related every polynomial they related with a subharmonic function, such that the Laplacian of that function is going to be this. And they exploited this connection and thoroughly investigated the subharmonic function to produce upper bounds. And Lewis and Wu used the same ideas as them to produce the best bound at the time. I don't think it's been, it's not much better. And I think if I remember correctly, that it's about half minus 2 to the minus 264. But in addition, Yermakov by himself, again, worked on it in the 80s because it was published in 91. He found also a lower bound. Here I should say this. Okay, wonderful. So now let me describe what is the connection, the specific connection that I'm talking about. And what I like about it is that it's literally the mean value theorem. Using the mean value theorem, we know that if we try to look at the difference between the distance of the image divided by the distance of my 2 points, this is going to be equal to the derivative at some specific point in between. Now, the first thing you're going to tell me is, wait, you just told us that phi is not defined up to the boundary. So what are you doing here? Well, Kobe says that it's fine. And this is one of these places when I say vague things. Yes, Oleg, I'm looking at you. I'm saying vague things, and I will continue to say some vague things throughout the talk, because if I would say everything precisely, we wouldn't be able to get to the point. All right? So I'm going to put absolute value here. And I'm going to write Kobe said it's fine. Someone wants to know the intricacies of the, we can talk about it later. But the point is, if I go back to my map and I choose 2 points, say Z and W, and I drew this in red, so this will correspond to this red arc here, right? Well, let's see. So this is Z and W, and so this is going to be phi of Z and phi of W. And I'm going to draw a disk precisely around this little arc. What do I see? I see that the diameter of this disk is roughly the distance between phi of Z and phi of W. I'm going to write it if the diameter of the disk is kind of roughly like the distance between the points, and if the harmonic measure of the disk is kind of like the distance of this arc, then what do we get from this? If I plug it in here, I'm going to replace the numerator by lambda by the diameter of the disk. And I'm going to replace the denominator by the harmonic measure of the disk. And this is kind of like the derivative at some point, which for now I'm going to call it ZB because it depends on the disk. So what does this give me? This gives me a connection between the way that the derivative grows near the boundary and the decay of the harmonic measure. And this observation was done by Alforth in the 30s, but relating this observation with this spectra was done by Makarov. Okay, what does it give me in terms of F and D? Well, in terms of F and D, what I'm going to get is, well, instead of associating for every disk B, well, now in every B, I only have to find this arc that satisfies these 2 conditions. So my arc will be whatever IZW is going to be this arc ZW. If inside every disk I can find such an arc, then definitely I have the derivative. So I did a reduction from that hard problem for this. And evidently this is true sometimes. So theorem 1, this is folklore. It's been known for a long time in some way. If omega is a quasi-disk, so it's of course simply connected, bounded, and it's a quasi-disk, which means it doesn't have inwards cusps or outwards cusps. Everything is like nice and well contained. Well, then I get from this argument that 1 minus A, the dimension spectrum of 1 over 1 minus A, is always dwarfed by the distortion spectrum at A. And in fact, we can say even more. We can say that if A is a growth point, what I mean by that is that the function actually changes value in a neighborhood of that point. It's not constant. Then you get equality. Maybe the first question is, okay, can we maybe have equality always? So the first answer is no. Already Makarov in his work showed that it's not possible. He showed a set where this is an inequality, a strict inequality. So the next question is, okay, but can it Can it always be a weak inequality? Would one always be true? And that was believed to be true for many, many years, since the 90s, basically. But apparently what I'm going to show you now is that it's not true in general. And the way we're going to do that is exactly defy this if thing here. So we're going to defy the yellow box. So maybe we'll start with an idea. Why would this be defied? Well, let's go back to the anglerfish example. And instead of looking at this pink disk, let's look at the disk, which is actually centered here. So if I want to center something here and I want to take, say, most of the yellow curve, it's going to be a very crooked disk, but bear with me. So I'm going to draw a large version here. So we have the yellow arc, and the yellow arc looks like this. Or maybe I should like this because this is the center of my disk. And the red arc looks something like this. Now, the harmonic measure of the red bit is much, much bigger. And so you see that the harmonic measure of B, if this were my B, the harmonic measure of B behaves like the harmonic measure of the red guy. But the diameter of B behaves like the yellow guy. Now you're going to say, okay, maybe double the disk. If you double the disk, maybe it works. But no, what happens if I double the disk? If I double the disk, what's going to happen? I'm going to pick up now a huge chunk of measure. So suddenly my harmonic measure is huge. So that's not helpful. So you might say, okay, well, what about taking more of this curve? Well, if I try to track this curve and pick up enough harmonic measure, I will have to have a huge diameter because I have to climb a lot inside this tube. Now, this phenomenon is not new, but somehow most people in the field assume that, starting from some point or some scale, or maybe I'll have to throw out a set of dimension 0, like we saw that sometimes we do, then it should be fine. This could not occur too much, but evidently it can. And so the first example, I call it the feisty Pac-Man. You draw a Pac-Man and you start, the upper lip is going to be smooth. But then the lower lip is going to have, some teeth. Okay, and let me focus on one of these teeth. So if I take a disc, a circle here, what does that look like? I have a tooth. And I'll draw in red passes like this, yay close. Maybe say close enough, but not too close. And then here you can draw a sequence of discs such that they kind of replicate the same phenomenon. So if I try to now draw just one of these discs have in the center this part of the boundary, and then kind of like brushing it, something that comes from the top. So you can see it's the same phenomena as the anglerfish had. And if you choose the scales just correctly, then you have enough discs in every tooth to pick up the Minkowski. But it will fail to satisfy these ifs, and indeed, you will get a reverse inequality. And so this is one of the first results. For every a that you give me between 0 and 1, there exists a simply connected bounded domain with 1 minus a f omega over 1 minus a, strictly bigger than the omega of a. And our first intuition was to say, well, definitely it's Minkowski's fault. Like maybe if we look at Hausdorff dimension, this will work out. And if you remember the beginning was, well, I need to measure this and Hausdorff is too hard, so I'm going to use these Minkowski guys to help me out here. And so it kind of made sense to say, okay, maybe we have to jump into Hausdorff. But in fact, we have another counterexample that I will not describe that creates this phenomenon over and over again near the. So what you get is you get that 1 minus a, the Hausdorff dimension of my set W harmonic measure and A still satisfies the inequality. Right? And this is a set of dimension almost 1. So you can't get 1, but you can get as close to 1 as you want. Okay, so let me just briefly say what we can do. So this puts a dent on our relationship and on the whole theory. But what we did manage to
Sorry, I got a little bit lost. What was d omega of A again?
the omega of A shows up here. That's the distortion spectrum.
Ah, it's it's
It's the guy where the derivative is big or positive.
sorry, it's in red of that. Yeah. Okay.
So what we can do is sometimes you don't need a bound per set. Sometimes you want something uniform. And so what we can do is what's called a universal guy. And slightly sad that I can't say a lot more about this, but if you define D of A to be the supremum over all simply connected bounded domain of D omega of A, and you have the same for F, then we can say that these satisfy inequality here, just like in theorem 1. And I'll just say briefly why it's true. It's true because we were able to have some kind of approximation theorem for any domain by finite iterated function systems, or some generalization of the Koch snowflake, right? And that allowed us to do this. And the reason why it's new is because so far the people only thought to approximate the distortion spectrum because they believe that the inequality is true. So why bother with the dimension spectrum, which is harder to approximate? So this is the first time that the dimension spectrum is also approximated with finite iterated function system. And if you'd like to hear more, I'll be happy to talk about it. But I think at the 1 minute that I have left, I'd like to tell a small anecdote maybe. Alec is actually a family friend. I met him first time, I want to say over 10 years ago. I was doing non-amenable ergodic theory at the time, and the thought of giving a talk at his birthday conference would have been very surprising for anyone, I think. But somehow, as years passed, my group of interests both converged and diverged with Alec. And now I want to say he's already accustomed to getting frequent emails from me with questions and ideas. I hope very much to be here in 10 years. So thank you.